This image shows a damaged integrated circuit captured by a scanning electron microscope at 2500 times magnification. When analyzing components at this scale, engineers have to deal with intense microscopic texturing and high-frequency noise. Trying to clean up that noise using standard spatial convolution, calculating averages pixel by pixel, is computationally expensive. It's a brute force approach to a structural problem. Our target is to reach this state. We need to smooth out the microscopic noise without destroying the underlying structural geometry of the circuit components. To achieve this precise level of smoothing, we have to bypass spatial limitations entirely and translate the image into the frequency domain. Treating visual artifacts purely as a grid of spatial pixels is inefficient. True engineering control requires us to view the image as a composite of mathematical frequencies. This flowchart outlines the three-step computational pipeline required to execute this bypass. The first step takes the original spatial image, our f of xy, and converts it into its Fourier transform representation, labeled here as f of uv. Next, we multiply that transform data by a specific filter function, h of uv, to isolate the exact data ranges we want to keep. Finally, we pass that filter data through an inverse Fourier transform to rebuild the enhanced spatial image, g of xy. This pipeline allows us to target and isolate specific variables, like texture and noise, that are completely physically entangled when viewed in the standard spatial domain. Instead of guessing how to patch neighboring pixels, the frequency domain turns image correction into a strictly objective mathematical operation. This diagram illustrates the core premise of Fourier's theory. Any periodic function, no matter how complex it looks at the bottom, can be represented as a weighted sum of simple sines and cosines, shown as the individual waves above it. Because digital images are simply two-dimensional discrete signals, we scale this idea up using the Discrete Fourier Transform, or DFT. The equation maps spatial pixel coordinates, x and y, into a new grid. In this new coordinate system, u and v represent specific horizontal and vertical frequencies. On the left is a simple spatial shape, a white rectangle. On the right is its two-dimensional Fourier spectrum. Notice how the sharp physical edges distribute their energy outward along the horizontal and vertical axes in the frequency grid. The DFT translates physical geometric shapes into pure wave data without losing any original information, setting the stage for precision filtering. This is the actual Fourier spectrum map for our damaged integrated circuit. To read this map, you look at the magnitude, which indicates the strength of a given frequency. Stronger frequencies appear as brighter white pixels. The map follows a strict geographic rule. The low frequencies gather at the exact center, or origin. These represent the smooth areas and general illumination of the image. As you move outward, you reach the high frequencies, encoding sudden transitions. Looking closely, the sharp 90-degree physical angles of the IC chip create these prominent high-frequency spikes radiating outward like a star. The spectrum map physically separates the general, smooth forms of the circuit from its microscopic, sharp details, making them easy to target. To filter the image, we multiply our original transform, f of uv, by a filter function, h of uv. This yields a new filter transform, g of uv. This 3D plot illustrates the ideal low-pass filter, the exact mathematical tool we need. It works based on a strict radius logic, establishing a specific cutoff distance, d sub 0, from the origin. Any frequency values falling inside this central radius are multiplied by 1, leaving the smooth structural data intact. Values falling outside are multiplied by 0, instantly deleting the edge noise. The ideal low-pass filter acts as a geometric scalpel. It excises only the outer spectrum noise while leaving the core illumination untouched. When we drop this mask over the SEM spectrum, we isolate the low frequencies directly in the center. This visual masking represents the literal zeroing out of the high-frequency components from the image data. The final step in the pipeline is to pass this newly masked spectrum back through the inverse discrete Fourier transform equation. Because the Fourier transform is a completely reversible process, we can collapse these modified frequencies back into a standard spatial pixel grid. Here is the reconstructed spatial image. Because the edges and noise were zeroed out in the frequency domain, the resulting surface is completely clean. Removing high-frequency wave data mathematically forces the spatial output to become smooth and continuous. We can test the robustness of this theory by inverting the math to create a high-pass filter, shown in this 3D plot. This function does the exact opposite. It drops the center low frequencies to 0 and keeps the outer high-frequency edges. This image shows the spatial result of that high-pass filter after running the inverse transform. Stripping away the smooth low frequencies leaves nothing behind but the sharp structural outlines and the surface noise. The frequency domain shifts image processing from a game of guessing local pixel edits to one of global mathematical isolation. It proves that visual artifacts are not permanent flaws bound to specific coordinates. They are specific frequencies that can be cleanly and objectively